last time we saw how to solve any nth order linear homogeneous differential equation. Now let's go back a bit, let's backtrack a bit and see what exactly are linear differential equations. Let's recap this a bit. So as we saw before, we're gonna have y, okay, gonna have y prime. You go all the way up to the nth derivative. Suppose it's the n minus 1th derivative, this is the nth derivative. All right, so you have all of these added, and all of these have can have coefficients. Okay, they can have coefficients, but those coefficients must strictly be functions of x. These y terms, the coefficients must strictly be functions of x. Suppose that this is a sub n minus 1 of x, and this is added, and suppose that this is a sub 0 of x. That's because this is the 0 derivative, and it's going to be equal to some function of x. On the right side too, you're going to have just some function of x. So this is a linear differential equation, okay? And what we were solving until now were these, okay? Well, not these. What I mean is we were solving linear homogeneous differential equations with constant coefficients. So first thing we said that, okay, so the right side, this is going to be homogeneous. This is going to be homogeneous if the right side is equal to 0. If f of x is equal to 0, then this is a homogeneous. Okay, I'll write that. So homogeneous. So, and also we were only dealing with the version where we, the coefficients, all of these were constants, right? So something like this. Let's say, actually, let's use capital letters. They're just some constants. Okay, there's just some constants. Okay, so something like this: a sub n minus 1 x, and all the way up to well, we're going back, but anyways, a sub 0. Then you have, wait, did I forget the n minus 1 derivative here? Okay, so n minus 1 derivative, this is y, and all of this is equal to 0. The right side must be 0. There can be no like standalone constant here. All right, so this was a linear homogeneous differential equation with constant coefficients. Now let's see the other case where well, we're still going to deal with constant coefficients. Okay, our coefficients will still be constants for now. But let's see what happens when this is not equal to 0. Well, when f of x is not equal to 0, this case is called, when this happens, we call it a linear non-homogeneous differential equation. So I'll write that down. So this is well, this is definitely linear differential equation because it came from our general linear differential equation, but this is non-homogeneous, okay, because the right side is not equal to 0. It's some function of x, okay. And now, before going into how to solve these and all these, actually those will come, will be for later videos. Today I just want to discuss a theorem concerning these, which we will use to solve these. It's pivotal to solve these non-homogeneous linear differential equations. And that is, suppose say that I know a solution, okay, some solution to the homogeneous, but suppose say this well, let me write it. This is a linear homogeneous differential equation. Suppose say we had kind of like the same non-homogeneous differential equation. Suppose say we had a non-homogeneous differential equation with all the coefficients and all of these are the same. Okay, except, well, on the right side, since this is non-homogeneous, it's going to be some function of x. Okay, now this is a non-homogeneous, this is non-homogeneous, and this is the homogeneous differential equation that we can kind of like derive from here if we just set the right side to 0. So this is like the related homogeneous differential equation, linear homogeneous differential equation. Now what am I getting at here? There is a theorem concerning these. If I have a solution, okay, suppose say y sub n is non-homogeneous. Okay, if I have a solution to the non-homogeneous differential equation, and I also have a solution to the homogeneous differential equation. Suppose say I also have a solution to this. Let's say y sub h, then the theorem is that the sum of these two solutions, okay, the sum of these two solutions, suppose say y sub small t, let's say, okay, the sum of these, suppose say y sub nh plus y sub h, the sum of these is also going to be a solution to the non-homogeneous differential equation. Okay, we know for a fact this has to be by definition, but what we are saying is even if we add any solution to the corresponding homogeneous differential equation, okay, to the non-homogeneous solution, where it's still going to be a solution, to my non-homogeneous differential equation. So let's try to prove that. Now, this is something that we did before too, something similar. What does it mean to be a solution? Well, since we are saying that y sub h is a solution to this this equation, well, it must satisfy this equation, right? If we plug it in, this must satisfy this equation, right? So what we can say is, if I write it here, a sub n, okay, so we had the nth derivative, but it's, we are substituting y sub h. It's the nth derivative of y sub h, okay, and this is a sub n minus 1. This is the nth derivative, n minus 1th derivative of y sub h, okay, and we have all the terms in the middle. We're gonna have a sub 0, just y sub h. It's going to be equal to 0, right? This is going to be equal to 0. So let me reposition this well. Okay, so this is going to be equal to 0. Now we know for a fact that this equation has to be valid because we said y sub h is a solution to that homogeneous differential equation. Now, the corresponding non-homogeneous differential equation, we're saying that this is a solution, okay? We are assuming that this is a solution to this equation. So likewise, if I plug it in here, it must satisfy this equation, right? As you can see, the left side is completely the same, and the right side, there's just one teeny small difference. There's that function of x instead of 0. So let's actually write this down. It's going to be pretty much the same as this, except we're going to have f of x on the right side. So a sub n, and this is going to be the non-homogeneous solution. That's what satisfies this equation. So nth derivative plus a sub n minus 1 non-homogeneous n minus 1th derivative, and we have all the terms in the middle. A sub 0 non-homogeneous. It's going to be equal to some function of x. All right. Now, what happens if I add these two equations? What happens if I draw this big line here? If I add these, if I add all the terms on both sides, something interesting actually happens. Okay, well, let's try to actually add one row. One row right here, and we should be able to see the trend with all, column. We should be able to see the trend with all the columns. And well, what we're gonna get here, if we add these two things, if we add this column, is what? And I'll actually do it here. So you can factor out a sub n. And inside brackets, you're gonna have the homogeneous solution, the nth derivative of that. This added with the nth derivative of the non-homogeneous solution, right? This matches up. All I did is add these two things, and I factored the a sub n. Okay. Now, here's something interesting happens. Well, what is this? It's the sum of the n derivatives of the homogeneous and non-homogeneous solution, right? Well, the sum of the homogeneous and non-homogeneous solutions is actually this, test function y sub t that we're trying to prove that this is a solution to the non-homogeneous differential equation, right? And so, if I take the derivative on both sides, I could put a derivative here, and we know the rule with adding functions there. If we take the derivative, the derivatives are just added. Okay, we could even do the second derivative the same way, and I think you see the trend. This pattern is going to go on forever. So any derivative, this is going to work. The nth derivative of these two, if we just add them up, it's going to be the nth derivative of this test function of ours. So this sum right here is actually just the nth derivative of our test function, the nth derivative of our test function. Now, we can replicate this here. We can replicate this here. So this is, as we saw, it's just a sub n multiplied by the nth derivative of our test function. See, similar things happen here. Similar things happen with all the rows. This a sub n minus 1. Here we're going to have the n minus 1th derivative of our test function. And, we have all the things in the middle, all the terms in the middle. They're going to be dealt with similarly. And here we have a sub 0. We're going to have the test function, the 0th derivative of that. And this is going to be equal to 0 plus f of x is just f of x, just f of x. Now, what did we find here? Well, we are saying that these two must be valid, right? These two must be valid equations because we assumed that these two functions are, solutions to this and this respectively, right? So if these two are valid, if I just add them, if I just add these two equations, well, this also has to be a valid equation. But what does this equation tell us is that y sub t, okay, our test function, actually satisfies the non-homogeneous differential equation, right? Okay, we have f of x, just f of x on the right side, and the left side seems, it seems to match the non-homogeneous differential equation too. So everything matches up, and that means that if I just substitute, our test function here, okay, it satisfies this equation. So y sub t must be a solution, right? So I'll actually change color here. So y sub t is a solution, right? I'll actually write it's a solution to a non-homogeneous differential equation. Okay, it's a non-homogeneous solution. It's a non-homogeneous solution. And well, this is interesting. This is interesting. Now comes the most interesting part here. Well, what we just proved is that even if we add the homogeneous solution to a non-homogeneous solution, it's still going to be a non-homogeneous solution. Now now we're going to see something a bit more interesting, which we can get from here. Well, in general, suppose say, I can do this because we have learned this already. Suppose say that we find the general solution to our homogeneous differential equation. I'll call that y sub gh, okay? Our general solution to our homogeneous differential equation, well, that's nth order, right? That's, the differential equation is nth order. So we're going to have n arbitrary constants here, right? N arbitrary constants, right? So how many, what was the order? What was the order of our non-homogeneous differential equation? Okay, this was our non-homogeneous differential equation. What's the order of that? Well, that's also n. And so the solution to this must have n arbitrary constants, right? All right, exactly n arbitrary constants. Okay, so this solution, the general solution to this, okay, the general solution to this must have exactly n arbitrary constants. All right, now something interesting happens. Suppose say I'm trying to find the general solution to our non-homogeneous differential equation. I'll call that sub g. And to be honest, I'm just going with these subscripts on a whim. I didn't prepare this beforehand. But anyways, so okay, suppose I'm trying to find the general solution, okay, to a non-homogeneous differential equation. All right, now and suppose say how many constants is this supposed to have? It's supposed to have n arbitrary constants, right? As we discussed, it's supposed to have n arbitrary constants. Well, I have done this. Okay, let's say that we're just forming some solution to our non-homogeneous differential equation. Okay, let's forget about this. Let's call this a another test solution. So, and the way I'm gonna form this is I'm going to not this. I'm gonna add the general solution to my homogeneous differential equation with some non-homogeneous solution, right? Some non-homogeneous solution. So I'll call that y sub p. Okay, y sub p, and I'll also add n there. Okay, so actually, now I might be wondering why, what's the reason for all these weird subscripts? Well, and this is what I'm trying to get at. So if I'm trying to find the general solution to my non-homogeneous differential equation, that must have n arbitrary constants, right? And as we discussed, how many arbitrary constants does this have? This has n, right? This has n. And this left side, which is the sum of this and something else, must have n arbitrary constants. So how many arbitrary constants should this have? Well, n, you're going to have n here, and we're going to have n arbitrary constants. We already have all the n arbitrary constants that we need here. So this one should provide 0 arbitrary constants, right? This one should provide 0 arbitrary constants. Also, that just means that this is a particular solution, right? This is a particular solution. That's why the P is there, okay? That's why this is a particular solution to my non-homogeneous differential equation. So I want you to recognize and understand basically what I'm trying to get at. Okay, so this is basically, I'll rewrite this. So this is y sub gn. So what this means is that the solution, okay, the general solution to my non-homogeneous differential equation is going to be the sum of the general solution of my, of the corresponding homogeneous differential equation. All I need to do is, take that non-homogeneous differential equation that I have and just set the right side to 0. I'm going to get a homogeneous differential equation. I'll solve for the general solution of that. Okay, I'll find the general solution of that. And with that, if I just add any solution, any particular solution to my non-homogeneous differential equation, I'll get the general solution to my non-homogeneous differential equation. Now, this is pretty interesting because, as we'll see later, okay, it's kind of difficult if we try to directly find the general solution to a non-homogeneous differential equation. These are much harder to deal with than the homogeneous counterpart. However, if we do it like this, okay, what's the advantage? We can easily find this. We at the very least, if the characteristic equation is something that we can solve, we can pretty easily find this. We know how to do that. And although it's difficult to find the general solution to a non-homogeneous differential equation, we often are able to find a particular solution. We can take a guess function, and there are quite a few methods to do that. But we can, a lot of times, quite easily find a particular solution. And so that's enough. That's really enough. We just need to take that particular solution, add it to a homogeneous or general homogeneous solution, and we'll get the general solution to a non-homogeneous differential equation. This is the method that we are going to use to find the general solution to non-homogeneous differential equations. And I really think that you should think about this, how fascinating and interesting this is. The non-homogeneous differential equation, we can just find the solution if we, take a particular solution to that and kind of like modify it by adding, the homogeneous solution, by adding a homogeneous solution. All right. It kind of generalizes this whole solution to make the general solution. So I want you to think about this. All right, so that should be enough for today. Next time we're gonna use this theorem to actually solve some linear non-homogeneous differential equations with constant coefficients.